Good evening, everyone. So, welcome to the third class of design, optimal design of game systems. So, we'll just go through, we'll have a quick go through of what we did in last class. So in the last class, we saw for a simple system of MM1 cube, uh, we fixed the service rate, which is the non-variable, and we um, made the arrival rate an unknown decision variable. So for these two types of for this type of setting, we designed two cost functions where one is the customer reward because now you have a control over your arrival rate. So you want to reward more number of people coming into the system and getting served. So we designed this customer reward as a linear with slope r, so it's lambda r. And then we designed waiting cost. Waiting cost was similar to what we designed last time, which is also linear. So if a customer uh, waits for time t, then he pays total of h into t waiting cost. But that is the cost to the customer. But the cost to the system is if in a unit time slot there are I people that stay are in the system, then the total cost that is incurred by the system is h into I, and the expected cost is h into expected total number of customers. This also can be written as expected h into arrival rate into expected waiting time using the Little's law. Mm, yeah, which we'll go into today. So in this type of settings where we design the optimal arrival rates, there is a reward and a cost. So what we do is we add the reward and subtract the cost and we maximize the reward. Whereas in the optimal service rate case, we saw we had two cost functions and we added the two cost function, minimize the cost function. So you could do any of this stuff depending on what your objective function is. Right. So if you have cost, then you minimize the cost. If you have reward, you maximize the reward. Uh, then we wrote down the optimization problem as maximize lambda belongs to 0 to mu. Here we have an extra one more constraint because lambda is less than mu. We can't take lambda to go to minus infinity. Lambda should be positive. So negative arrival rate means that something is going out of the server without getting served, which is physically improbable. Um, yeah. So now we have two constraints instead of one, which we had in the optimal service rate case. So now we have one constraint which is lambda greater than or equal to 0 and another lambda less than mu. We maximize the reward function. So first we saw how the reward function looks like some properties of the reward function. So we saw that when lambda goes to mu, one of the extreme of the interval, we saw that b lambda goes to minus infinity. And when lambda goes to 0, then we saw that it is 0. Right. So we know that it starts at 0 and goes to minus infinity. Now, uh, depending on different properties of the function, could always be negative or could go to positive and come back to negative. We thought could find out what that is. So we've calculated the first derivative of the reward function. The first derivative of the reward function and the second derivative. In the second derivative of the reward function, we saw that from the second derivative on the reward function, we saw that it is negative, which means it is a concave function, right? So if it is a concave function, the gradient is decreasing always. So now we need to see what is the gradient of the function objective function at 0. So if the gradient is positive, that means you have uh, the immediate values after 0, the reward function is positive, and then it keeps on decreasing because gradient is less than 0, and it again hits 0, the reward function, and then it goes down to minus infinity as lambda tends to mu. Right. So we need to find the cases where the gradient of the objective function at the point 0, is it positive or negative? It defines what the optimal is. If it is negative, then the optimal is 0. You can't do anything. If it is positive, then you can find the optimal solution by equating first derivative equal to 0, and we get the equation um, lambda star equal to mu minus root h mu by r, right? So you get cases where r is less than or equal to h by mu. For that, the optimal is 0. R is greater than h by mu, where the optimal is mu minus root h mu by r. So these both conditions we can write that lambda star is equal to max of mu minus root mu h by r comma 0, and we can simply notation consider as mu minus root mu h by r plus, right? So yeah, next, yesterday I was talking about social versus individual optimization, but before that, so yeah, I forgot to talk about yesterday was about an upper bound on the. Yes, so an upper bound on the optimal element, right? So let's write everything clearly once again. So today first I want to state the Little's law. So Little's law states that expected number of customers in the system equal to arrival rate into expected waiting time, right? So what this means is L lambda min. Here I'm writing both L as a function of lambda and min because that is more generic. But if you fix one variable and make the other variable unknown, then you'll have it up as a function of lambda or only mu. This is equal to lambda into W lambda comma. The L and W also depends on the scheduling policy that you fix. But for this first chapter, we are always considering the FIFO scheduling policy. So we are not writing it as a parameterizer of a FIFO, right? So what I mean is these two parameters also depend on the scheduling policies that we choose. But now, since it is fixed now, therefore I'm not parameterizing it here. I'm not parameterizing it. Okay, so yesterday we saw optimal arrival rate. We maximize the reward. So let me write the objective function once again, beta lambda. Now this here I'm writing it as a function of lambda because I know that mu is fixed, right? Is equal to r into lambda minus h into lambda by mu minus lambda. This I can write as lambda into r minus h by mu minus lambda, right? So now we know that lambda is greater than 0 because of the constraints from this thing. So we get E lambda is greater than 0 if r minus h by mu minus lambda is greater than 0, which implies if r is greater than h by mu minus lambda, then b lambda is greater than 0, and b lambda is less than 0 if r is less than h by mu minus lambda. Okay. Now, from the Little's law, we can see that this is equal to h into w lambda. I'm writing it as a function of lambda because I know that mu is fixed and lambda is the variable. Okay. So now just an observation here that the weighting cost that I have here, W lambda, which is equal to 1 by mu minus lambda. So in the case where we know that lambda is less than mu, right? If we keep on increasing lambda, then mu minus lambda decreases, and this all of this increases. So the denominator decreases, W lambda increases. So basically W lambda, the observation is that W lambda is an increasing function of lambda, right? Now, because W lambda is an increasing function of lambda, if R is less than or equal to H into W0, this implies R is less than or equal to H into W lambda, right? Therefore, lambda star equal to 0 because all lambda R is less than or equal to H W lambda. And this we saw yesterday. If R is less than or equal to H by mu, then lambda star equal to 0. And if R is less than or equal to H by mu, then this implies R is less than or equal to H by mu minus lambda. Because now I have decreased the denominator, so I have increased the total this term. So H by mu is greater than or equal to, so instead of writing this, let's write mu less than or equal to H by mu minus lambda. Okay. And when this happens, then beta lambda is less than 0 for all lambda, right? From this. So if R is less than H by mu minus lambda, which is H into W lambda, then we know that beta lambda is less than 0. So if R is less than H W lambda for all lambda, then beta lambda is less than 0 for all lambda. So if beta lambda is less than 0 for all lambda, then the maximum beta value that can achieve that is 0. So let me draw one more time. This is your lambda. This is your B lambda, right? This is your mu. And for all lambda that is less than mu, we have something of this one, right? So this is when R is less than or equal to HWC. If this happens, then this implies that R is less than or equal to HW lambda. If R is less than or equal to HW lambda, this implies B lambda is less than or equal to 0. If it is less than or equal to 0, the maximum that you can achieve is 0. Right. So now what we do is we restrict lambda such that R is greater than HW lambda. So R is greater than H by mu minus lambda. The second case, this case. So let me call this case 1 and case 2. So this is case 2 and now I'm doing case 1. If this happens, then we know that there exists some beta lambda such that beta lambda is greater than 0, right? So when beta lambda is greater than 0, what will happen is, so I will draw this graph again. This is lambda. But now beta is not always 0. It has some positive values, but it is also decreasing. So there can only be one crossing, right? For this crossing. So we need to find this crossing. So that crossing can be achieved by making b lambda equal to 0. Okay. So now we see that r lambda minus h lambda by mu minus lambda equal to 0. So the solutions to this are either lambda equal to 0 or r equal to h by mu minus lambda, which implies lambda equal to mu minus h by r, right? So now what we do is we define lambda star such that it is 0 if r is less than or equal to h by mu, or it is this term mu minus h by r, mu minus h by r if r is greater than h by mu. Because in this region, this lambda is positive. This is so b lambda is positive, right? In this region. So I'm calling this as this is 0. This is lambda bar. I'm defining this lambda bar as either 0 or this term. So basically, what this gives is if 0 less than or equal to lambda is less than lambda prime, this implies lambda equal to lambda star, which we derived yesterday. And that is mu minus root h mu by r. Mu minus root h mu by r. Right. And if lambda star is less than lambda less than mu, then lambda star this implies that beta lambda is less than or equal to 0. So what this means is lambda star would always lie somewhere before lambda bar, right? If lambda bar equal to 0, then there is no interval, then lambda star also be equal to 0. So lambda star and lambda bar would be. But if lambda bar is not equal to 0, then you have an interval in which beta lambda is positive. And if beta lambda is positive, then lambda star would always be strictly less than lambda bar. Right. So we have got an upper bound on the optimal arrival rates, right? So let me state this again. Lambda star is mu minus root h mu by r plus. This was our optimal bound that we derived yesterday. And the bound on this is mu minus h by r plus, right? And lambda star equal to lambda bar if r is less than or equal to h by, right? So if r is less than or equal to h by mu, what happens is mu is less than or equal to h by r, which implies mu minus h by r is less than or equal to 0, right? which implies lambda bar equal to 0. If lambda bar equal to 0, it implies that there does not exist any lambda belongs to 0 to mu such that v lambda is greater than 0. Therefore, lambda star equal to 0. So for this case, we saw that lambda star equal to lambda mu, and if r greater than h by mu, then lambda star is strictly greater than, sorry, is strictly less than lambda bar, right? Okay. Next, yesterday we discussed was the social optimal arrival, right? Where social optimal arrival rate is equal to lambda star that we found yesterday. Yesterday we were discussing also about the individual optimal arrival rate. Where social optimal arrival rate is we had the question we discussed about the question that is answered while designing of optimal system is who is the decision maker, right? It could be the uh, queuing system guy who handles the queuing system, handler of the queuing system, or it could be the customer. Now, then customer had two choices. This is social customer or an individual customer. So social customer means that I have a third person who looks at all the customers and then takes a decision so that the average reward that the customer gets is maximized, and the individual um, optimal arrival rate. In the individual optimal arrival rate, each individual customer takes the decision whether to join the queue or not join the queue. So before all this, we also had a discussion on uh, how to implement lambda arrival rate, right? So when we say that we have found lambda star arrival rate, so if we have found the optimal arrival rate lambda star, but how do you implement it? So what you do is you have a capital lambda arrival rate of customers which is greater than mu. So if you allow each all the customers to come, then all the customers who enter the queue, then it implies that the queue will become unstable. The queue would become unstable. So what you do is you select when a customer comes, you either allow the customer into the queue with probability A, or you reject with probability 1 minus. Or the customer maker, if customer is the decision maker, then so individual customer is decision maker, then either the customer agrees to go into the queue with probability A, or does not want to go into the queue with probability 1 minus, right? So in the case of an individual optimal arrival rate, the net reward that a customer gets is A into R minus H W lambda plus 1 minus A into 0, right? So if R is greater than H W lambda, then all the customers would want to, this implies that A equal to 1. So all the customers with probability 1 would enter the queue because you'll always get a higher reward, right? If R is less than H W lambda, then no customer would want to go to enter the queue. So if R equal to H W lambda, then it doesn't matter the probability, all customers get 0 rewards, right? Now, motivated by the concept of Nash equilibrium, we define something known as individually optimal arrival rate, or this also is known as equilibrium arrival rate. I'll denote this as lambda e. And for this lambda e, we'll have an associated AE into capital M, right? So lambda is, because it is equilibrium, the property that it will follow is no individual customer trying to maximize its own net benefit would have any incentive to deviate from lambda e, right? So what is follows is lambda e equal to 0. This implies A equal to 0. If A equal to 0, then lambda equal to 0. If R is less than HW lambda. R is less than HW0. If R is less than HW0, this implies that R is less than HW lambda. If R is less than HW lambda, this implies that A equal to 0. Okay, this is case 1, right? Next, when R is greater than HW0, then lambda E equal to A lambda, and this lambda E is equal to mu minus h by r, which we have defined, mu minus h by r. And if you calculate b lambda at lambda e, so if you calculate b lambda e, then you'll get this also as equal to 0, right? Because you have r minus h by mu minus lambda e, which is r minus h by mu minus mu plus h by r 0. Right. So if r is greater than hw0, then lambda equal to a, and where lambda e equal to mu minus h by r. Now, as you can see, the structure of lambda e is the same as the structure of lambda var, right? So lambda e is also equal to 0 if r is less than hw0 and equal to mu minus h by r if r is greater than hw0, which is equal to lambda. So the optimal arrival rate has two decision making. One is social and one is individual. Right. The social lambda star equal to mu minus root h c by r h mu by r. Individual is lambda hat, which is in mu minus h by r. Right. And since we have already shown that lambda bar is greater than lambda star, lambda bar is an upper bound greater than equal to of lambda star. We can say that the individually optimal arrival rate will be greater than or equal to socially optimal arrival rate. So what this means is, so intuitively it makes sense. So if each and every customer individually would want to maximize his own reward, then you would see a very high rate of customers going inside. But if someone from the outside decides who gets to go in and who doesn't gets to go in, so that the expected reward that all the customers in the uh, queuing system get the maximum reward, then you'll see that he'll allow customers at a lower arrival, or at least, which is at most the individually optimal arrival, right? So next we have a little theorem. The theorem states that lambda s would always be less than or equal to lambda e, the same thing that we stated here, right? And lambda s equal to lambda e equal to 0 if r is less than or equal to h by e, which we have derived here, right? Yeah, while deriving the upper. We saw that lambda star equal to lambda bar and both are equal to 0. And 0 is less than lambda s is less than lambda e if r is greater than h by e. And while deriving these three, we didn't use the fact of MM1 system anywhere. Not only true for MM1, but also GI1 queues also it is true. It holds strictly. So what are the properties that we used to show these upper bounds was W lambda is strictly increasing. right? 2. W lambda tends to infinity as lambda tends to mu. 3. W0 is equal to 1 by mu. Using these three conditions, you'll always get these things. So these three conditions are the general conditions which we use to draw these two graphs. Right. One graph was for the case R is less than HW0, and the other condition was for R is greater than HW0. Okay. So next one small section where we give some intuition on optimal arrival rates, the internal and external rates, right? So in this section, we'll see why is there a difference in the social and individual lambda optimal arrival rates. So what actually happens inside? Like, so now let's take suppose R is greater than H by mu, right? Then if you calculate the first derivative of the objective function, we get it as lambda R minus H into W lambda plus H lambda into W prime lambda. Now lambda S, which is equal to lambda star, this we got by equating R equal to H into W lambda plus H lambda W prime lambda, right? If we do this, what do we get? Let's check this out once. R H by mu minus lambda plus H lambda by mu minus lambda whole square minus R equal to H into mu minus lambda by H lambda. By also this is plus. Right? This was our lambda star. So we found lambda star when we equated these both. So you have two terms. In the objective function, you had two terms, and you what we did was we calculated the rate of change and we equated the rate of the increase in the rate of change of one is equal to the decrease in the rate of change of the other. Right? And for so from this, and how do we found lambda e, which is equal to lambda bar? We found by equating h w lambda to r. right? So what does this mean is H this is your lambda one, right? So we can interpret uh, this term H into W lambda as internal effect, and this term H into W prime as external effect. So H into W lambda is the internal cost borne only by the customer when the arrival rate is lambda. If he joins, then this is what he has to. On the other hand, the quantity H lambda W prime is a marginal increase in waiting cost incurred by all customers. So this is incurred by all other customers as a result of marginal increase in arrival rate. So what this means is because of a customer choosing to join the queue, there'll be a marginal increase in the arrival rate. That marginal, because of that marginal increase in the arrival rate, the waiting cost that all the other customers have to pay is denoted by this term. And the effect of just any customer who is in the lambda rate join, then the waiting cost is paid by this term. So when a socially mm, optimal decision maker takes the decision, he takes into account the internal effect, that is just the pure the customer, and also the effect of other customers joining in the queue, and then he calculates the optimal. But when an individual customer uh, individually optimizing customers' failure, it doesn't take into account the external effect of its decision to enter. The formula lambda E takes into account only the internal effect of the decision. So it only takes the customer's own waiting cost, right? But in contrast, lambda S takes into account both the internal effect and the external effect. So individually optimizing customers can induce to behave in a socially optimal by charging each entering customer a fee or congestion toll equal to the external effect. So you can make lambda S to be as lambda E by charging um, each customer a toll that is equal to the external effect, H lambda W prime lambda, right? In this way, the arrival control can be decentralized. So you do individual control, but then you ask the people to pay a toll, which is equal to H lambda lambda prime W prime lambda, right? So here one more observation is that here we are all dealing with W lambda, right? These all internal and external effects hold for any W lambda, um, where W lambda is a well-defined function which satisfies the properties that were stated in 1, 2, and 3, right? If W lambda is a well-defined function and satisfies these 1, 2, 3 properties, then we can say that these general internal external effect holds. An example of that is MM1Q, where I've shown that these things hold. The intuition that we are following through holds, right? Okay, so next, so this completes the optimal arrival rate. So till now we have seen design of queuing systems for optimal service rates, optimal arrival rates. Uh, so now so for today, I'll keep this class short. The next class, we will see optimal arrival rate and service rates. I'll just give a brief introduction of what we'll see in the next class for optimal arrival rates and service rates. So if we consider the queue M, M1, in which both the arrival rate which is lambda and the service rate mu, both of these are decision variables. So both are unknown. Then how do you design the problem? So we'll use reward cost functions similar to what we have used in the arrival rates. So now we'll write the objective function as a reward based function. So now it is dependent on both mu and lambda. So you have an arrival rate R linear. There is a reward R per entering customer. So that expected reward is lambda into R minus H into, right? This is the waiting cost per unit customer in the systems, L into lambda and mu, since the waiting time depends both on arrival rate and the service rates. So lambda and mu. And then a service cost, C per unit time per unit of service, right? The constraint is 0 is less than or equal to lambda is less than. So before going to optimizing this, let's see some properties of the reward function. Let's see what B00 is, right? So for MM1 queue with FIFO queuing discipline, B00 is 0, correct? The waiting cost is 0 because there are no arrivals from null hypothesis. There are no arrivals, so no customers implies no waiting time, right? Lambda is 0, this goes to 0, this goes to 0. So B00 is 0. And note that B lambda mu has a discontinuity at 0, comma 0, right? If you write down the whole expression for B lambda mu, you get lambda R minus H into lambda by mu minus lambda minus C into mu. Here you can see the discontinuity if you substitute 0, comma 0, right? And here, under this constraint, we can see that this term, h lambda by mu minus lambda, is always greater than C, right? So let's put it to one side and we have lambda R minus C into mu minus h lambda by mu minus lambda. So you're subtracting some positive number. Now it depends on this. Now let us see how does lambda R minus C mu vary. So if we know that lambda is always less than, right? Now if R is less than C, less than or equal to C, then this term is negative. This term is negative, this term is positive, negative minus. You're subtracting something from some positive number from a negative number, then this will be less than or equal to 0. Right. Then the optimal solution is given by lambda star equal to mu star equal to 0. So 0, comma 0 is the optimal solution. So we'll assume C is greater than R, which implies that the service rate, the cost for serving someone is actually greater than the reward that you give the customer to just come and get service, right? And if we assume C greater than R greater than C, then we can exclude the point 0, comma 0 and just restrict our attention to lambda comma mu such that 0 less than equal to lambda less than mu. So now since this whole set contains pairs of lambda comma mu for which B lambda comma mu is greater than 0 and B lambda mu is continuously differentiable over this region because we have eliminated 0 comma 0 point. So we'll similarly follow the optimization problem of the first two and we'll derive the first order optimality conditions to identify um, the optimal pair lambda star and mu star, right? Now, once we have identified the optimal solutions for lambda star and mu star, we have to check whether the solution is feasible or not by checking the constraints. And even if it is feasible, you have to check second order conditions, right? To show that B lambda mu is jointly concave in lambda. If B lambda mu is not jointly concave in lambda mu, then um, you have no guarantee that the first order condition that you have used to find lambda star and mu star are actually the optimal, right? So these things we'll see in the next class. The optimal arrival rate and service rate, where both are variable. So now you have a multi-dimensional problem, and we'll get some insights. In the same way, we have got some insights on the optimal arrival rate and optimal service rate. Okay.